In the last video, I talked about how the hard step solution is excessively bad as a solution to the Fermi Paradox because it's based on evolution without understanding evolution. Today I'll be looking at game theory solutions. Most of these completely fail to grasp the game theory of space from the start. Instead of actually considering what space is like and what problems need solved, they try to guess at the motivations of aliens. This is like trying to understand why skunks have stripes by psychoanalyzing them. You don't need to know if these skunks are pessimistic or optimistic, or if they have a warrior culture, or if they're peaceful philosophers. They didn't choose the stripes chose them. Similarly, these models try to understand alien civilizations by making wild assumptions about their psychology and culture, when the actual constraints of physics and game theory would force certain behaviors regardless of what kind of music they like or whether they're religious. The Dark Forest and Grabby Aliens are especially guilty of this. They aren't just wrong, they completely fail to engage with the underlying premises. Let's start with the Dark Forest. The Dark Forest solution is that because an alien civilization can wipe you out with no warning, that means the best move to protect yourself is to eliminate any competition on detection, therefore everyone is hiding. Now let's not get ahead of ourselves. The Dark Forest is a plot device in a novel, and I don't want this section to be taken as criticism of the novel, but because it's being treated as a serious solution, I'm going to engage with it. Okay, to do any kind of damage to this target civilization, the first thing we need to do is get over there somehow. First, let's take a look at rockets. 1. They could use a fusion rocket, which will top out at 10% the speed of light, and be clearly visible. This isn't a sneak attack, so it doesn't qualify. 2. They could use an antimatter rocket. Hypothetically, this could reach 90% of the speed of light. Hypothetically, giving them much less reaction time. In reality, the magnetic containment of the antimatter is extremely heavy and energetically expensive, and this alone means that we're going to top out at 20% the speed of light, but it gets even worse. Antimatter annihilation is not like a bomb. It almost exclusively makes gamma rays, neutrons, and neutrinos. So while some of this will convert to heat due to gamma rays interacting with the rocket, and that can be used for fuel, for the most part it just goes through the rocket. Option 3. Some kind of exotic physics we haven't discovered yet. The thing is, if we haven't discovered it, that implies it interacts so weakly with atoms that the rocket equation dominates again. And obviously this doesn't get into how at these kinds of distances, course correction starts to dominate the rocket equation rather than acceleration or deceleration. Another option is to use a mass driver to fire a projectile at nearly the speed of light so they can't see it coming. To put this in context, let's say our target star is 1,000 light years away, and our projectile goes at light speed. This is a 2,000 year difference between when we measured it and when the projectile will arrive. Now, most stars go between 20 and 100 kilometers a second relative to our sun, meaning in this time frame it will have moved between 0.2 and 1 light years from where we observed it, or 200 to 1,000 times the radius of its heliosphere. In addition to this, the star does not have a constant velocity. It is also bobbing up and down in the galactic plane, and is being affected by all the other stars' gravity surrounding it. For example, over this time period, our sun will be moved by 100 kilometers by Alpha Centauri. This is an immeasurably small effect on these kind of scales, but it does alone show that this is an n-body problem. In addition to all these forces changing the path of the star we're trying to hit, they're also deflecting the projectile, which also has to deal with gas clouds and random rocks that might deflect it, where the slightest deflection will add up to a ton over 1,000 light years. But even more than this, the planet we're trying to hit doesn't have an elliptical orbit. It's affected by the gravity of all the other planets in the system. We can't even tell what general shape this orbit has from our perspective because we can only get enough light to see the planet when it's transiting. Okay, but these aliens have an oracle machine that can just solve this no problem, so we can treat this as a stationary target. So to hit an Earth-sized target from a distance of 1,000 light years, you will need your mass driver to have 12 digits of angular precision, or you will just miss the planet entirely. This is equivalent to moving the tip of a barrel of a gun by less than the width of an atom. Quantum effects dominate and you can't do it. Okay, but what if we just lengthen the barrel to increase the displacement? Well, to get this to the kind of macroscopic scale you need, about 10 nanometers, it's going to need to be 5,000 kilometers long, and it needs to be perfectly straight, and the tip has the same problem again. And this is all while it is experiencing enormous magnetic and thermal forces for the launch. Also, the launcher isn't still relative to the frame of reference the target was measured in. Rather, it is always accelerating, either falling into its own star or orbiting it. Alright, yes, but these are tricky aliens, and they have added a fusion rocket to their projectile to course correct it. In addition to the incoming sensor data being so red-shifted in the back that it can't make anything out, and so blue-shifted in the front that it's mostly X-rays tearing the system apart, the relativistic effects mean that the fusion fuel is roughly 1/7 as effective as it otherwise would be, due to either time dilation or relativistic mass, depending on your frame of reference. Additionally, the fusion rocket is less precise than the mass driver. So for the first leg of the journey, you can't even course correct at all, as you would do more harm than good. And by the time you can, you're already so far off target, corrections are futile. Also, the light made by your fusion rocket will be extremely blue shifted from the perspective of the target, and for a K1 civilization, easy to pick up on the cosmic background radiation detectors they already have. The solution for all this, used by the book The Three Body Problem, is that the aliens are on Alpha Centauri and only 5 light years away, actually close enough to hit us. So for the very rare exceptional case where 2 planets with life just happen to be in striking range, this is a viable solution. But I hear your objection. You can still sneak attack the other system. Yes, there are 2 ways to transverse space, straight line or scenic route. You can either go directly towards the target star, which is impossible at galactic scales, or you can make sort of shorter hops from star to star until you reach the destination. The key insight though is that this fundamentally changes the game theory. In Dark Forest, civilizations stay hidden because they fear instant retaliation from anywhere. But if attacks require physically traveling through multiple star systems, it creates a detection radius around each civilization. You can only be threatened by civilizations within 1 jump from your location, and you'll be able to detect them moving through neighboring star systems long before they reach you. This transforms the prisoner's dilemma structure that makes Dark Forest compelling into a different strategic game entirely. Part 2, Grabby Aliens. So now that we understand the basics of sending objects between star systems, let's take a look at Grabby Aliens. Here, instead of trying to hit the planet with a projectile, we're trying to get a probe into the heliosphere and clone our civilization. For targeting, we need to hit a fairly wide radius, about 4 AU for G-type stars and about 0.4 AU for red dwarfs. The precision requirements for the mass driver are 5 degrees of precision to get us to 362 light years, and 6 to get us to 10 times that, etc. This is for hitting a G-type star. For a red dwarf, it will be 1/10 of this. And the actual target zone is actually much smaller than this because of stellar gravity. So the solution to that is just spam it. Now that we know their target, we need to figure out how we're going to decelerate. Option 1. We can use a Bussard ramjet and solar wind to kind of decelerate by about 0.03 the speed of light. Alternatively, we can use the heliosheath, which is a thicker density of particles, to decelerate by 0.1 c, but in this case, the sunlight at this location will be too weak for our solar collectors. Also, we know the heliopause is within a 40 to 50 AU radius of the star, but it's only about half that size, and we don't know exactly where it is due to turbulence. So it looks like we can't use external factors for help. We'll need to use internal energy source to stop. Now previously I gave some ballpark figures for fusion antimatter rockets, but let's put some hard numbers to it. Now I don't understand the rocket equation too well, so I'm just going to use conservation of energy for this. What we do is set the relativistic momentum equal to the energy of the fuel and solve for velocity. That'll give us the maximum velocity we can go at before we can no longer brake. Easy, right? As you can see for antimatter, this is 86% C. For deuterium-tritium fusion, it's 11% C, and for lithium-deuterium fusion, it's 4.3% C. Now, you're wondering, why would you use lithium fusion instead of tritium if it's slower? Well, it's because tritium will quantum tunnel out of the fuel canister and you'll be out of fuel by the time you arrive. But when the lithium and deuterium are reacted together, they're a solid. You can keep track of it. So this puts the effective speed limit at 4.3% C. But hey, this is slow enough that we can reliably use a gravity assist to brake, meaning that for approaching a G-type star like our Sun, we can get up to 10% C, and for getting near a hypergiant, we can get to 20% C. But for a red dwarf, we can probably only get to about 2% because, well, the previous speed limit didn't account for the actual mass of the rocket. Remember, the slower we go, the more dated the targeting data and the more the targeting becomes a potential issue. Okay, now that nobody's confused about what's going on here, let's take a look at how this solves the Fermi Paradox. Well, we can estimate how many Grabby civilizations there are with the hard steps model. You may have seen the biological papers saying why there's no evidence of the hard steps, but luckily this has not dampened the credibility of the model at all, because proponents obviously know more about biology than people that study biology. The aliens expand in a sphere at a speed greater than 30% the speed of light. It's a sphere because the author doesn't know that all the stars move relative to each other. And while you may think that this misconception makes sense for a random internet theory, an academic can literally just walk across the street to the physics department and ask. And they prevent other life from forming because, well, if they didn't, that wouldn't solve the Fermi Paradox. This may sound circular, but the important thing is it's kinda scary, and that makes it very credible during peer review. Now obviously we need to figure out, what do they gain from this? Well, based on demographic data, we know that for humans, we expand based on lack of access to birth control. So we have aliens that have figured out Dyson swarms but are still ironing out family planning. So because of this, these aliens have a problem. Infinite growth, finite solar system. Because this is just neoliberalism in space. If you don't know what neoliberalism is, there's different kinds of capitalism like classical liberalism, neoliberalism, embedded liberalism, orodo-capitalism, social liberalism, etc. This is why boomers all think capitalism is fair. When they grew up, the country used embedded liberalism, which is just a different system. We've used neoliberalism since the 70s. Anyway, the author uses space neoliberalism to build a pessimistic model of exploitation for the sake of exploitation and creating markets for the sake of having markets to expand into. By using this, he can say, I'm just doing the math to justify his own pessimism. Now this may sound circular, but the important thing is the author doesn't have to admit there might be something wrong with his ideology. So anyways, the alien solution here is to make probes that go to other stars to clone themselves who take thousands of years to send a message back, and have no discernible way to send resources back. This is the economic equivalent of trying to solve your household budget problem by getting pregnant and putting the baby up for adoption. Now, speaking from my personal experience of being born from a clone tube with no family, and told to colonize a hot Jupiter with no supply line for the benefit of some weirdos I never met, I felt quite resentful. However, these aliens don't have that problem because they're all brainwashed drones. You may be wondering at this point, how does copy-pasting their problems across space even count as expansion? Well, what matters is their genes are spreading, so that one stellar event can't cause extinction. This makes a lot of sense as a motive. Generally, when a disaster strikes, people are more worried about the gene pool than their friend's safety, and this would be the same for aliens because, much like us, they evolved in a sort of platonic space and not some kind of small band or tribe. Besides, trying to spread their civilization by spreading their ideas clearly doesn't work. Consider, for example, that even here on Earth, there's no example of two members of the same species fighting, or if different species work together. So we can reach these conclusions. Genetic lineage matters above all else, cultural transmission is irrelevant, success is measured in genetic propagation, and exterminating all other life is logical. Because the author saw an episode of Doctor Who one time and found these Daleks super convincing. Regardless, we now know these Grabby Aliens must exist because no aliens are visible, and that means we're early because if we weren't early we'd see them. This may sound circular, but you can do the very scientific test of waiting several billion years after we're extinct to find out if it's right. The important thing is, the author gets to feel smart. The most disturbing thing here isn't its circular logic, its impossible physics, or its economic absurdity. It's that it's essentially Darkseid's anti-life equation dressed up in academic credentials. And I know, okay, the universe doesn't care about morals. Facts don't care about your feelings. It's always fun to say those things, isn't it? It's fun to say, history is written by the victors, or isn't it a crazy coincidence that good guys always win? Because cynicism is just the same as wisdom, isn't it? I'm gonna let you on a little secret here though. Countries without slavery simply outperform those with slavery. Economies grow from the middle class, and in terms of women's rights, you don't rule the world when half your human capital is illiterate. And most damningly, altruism didn't evolve multiple times because evolution is a naive Pollyanna. But Grabby Aliens ignores empirical reality in favor of baseless assumptions that cynical paranoia and aggressive expansion must be optimal because it's the most cynical idea, and that must be right. That's just doing the math. That's just cold equations. Grabby presents mathematical proof that preventing all other life from existing isn't just rational but necessary for survival, and is treated as a serious analysis. The theory requires civilizations to be simultaneously advanced enough for relativistic travel yet too primitive to solve basic management problems, all while assuming that aggressive expansion with no return on investment somehow helps them. The success of this idea in spreading reveals something disturbing about how we evaluate credibility. When a model stimulates the amygdala, or by presenting cosmic threats, inevitable conflict, and paranoia as mathematical certainty, it makes it feel credible to us. Our fear response makes paranoia read as rationality and pessimism as realism. That's how this junk passes peer review, despite its circular logic and impossible physics. It's not compelling because it's correct, it's compelling because it's scary. By dressing existential terror in equations, it bypasses our critical thinking and gets treated as serious analysis rather than what it actually is. Campfire stories pretending to be science. Tune in next time when I solve the Fermi Paradox.